Is now starting. All attendees are in listen-only mode.
Good morning. For those of you that don't know me, I'm Woody Cash, SCTE Golden Gate Chapter Knowledge Content Officer. Today's presentation is DOCSIS Showdown, key differences between DOCSIS 3.1 and 4.0. When DOCSIS 3.1 came about, the integration of OFDM and OFDM-A was a game changer, allowing operators to offer much higher speed tiers and at the same time improve reliability. But DOCSIS 4.0 brings even more features. Today's presentation will compare and contrast the differences between 3.1 and 4.0. Today's presenter is Brady Volpe. Brady has many years of experiences in the broadband field working for Secor, Sunrise Telecom, and Viavi, and is now the CEO of the Volpe firm. Before we get started, I'd like to cover some of the benefits of SCTE membership. For our Golden Gate chapter members, you can get paid to certify. Please see details on our website. For those of you in other chapters that are in attendance today, please check with your local chapters to see if they have a certification program. In addition, the SCTE has a vast catalog of courses. I would just look at these courses a few weeks ago, and yeah, there is a lot. So if you're one of those people that likes to take in and develop your knowledge, this is the place where you can do it. In addition to the full courses, we have micro lessons, lightning mobs, and primers. These are short lessons that will help you refresh your technical knowledge and also prepare you for SCTE certifications. I'd like to take a moment to also promote our YouTube channel. Golden Gate Chapter now has a YouTube channel. On our YouTube channel, we have a few past webinars. We also have interviews of our Broadband Founders Club inductees and interviews of our board of directors. So you get to know who are your board of directors. Upcoming chapter events, board nominations and election timeline. So we have, in the next few days, you will receive an email in your email box. This is for Golden Gate chapter members. And you'll get a chance to vote on your next board of directors. On October 1st, election results will be shared with the board. And November through December, we'll have a transition period where the income board members begin onboarding and role assignment. January 2026, we'll make a public announcement and introducing everyone to the new board of directors. Upcoming webinars, 10/7, we're going to have the nuts and bolts of FDX with Frank Eichenlaub of Comcast. 11/4, powering critical infrastructure with EnerSys. And in December, first week of December, typically, although the date might change, but we have our fall training summit. So we will have all the California chapters and at least 2 of the Florida chapters will be presenting various webinars for about 6 days. So you can catch up on a lot of training by the end of the year. So without any further ado, I would like to get Brady on here and we'll get this presentation started. Welcome, Brady.
Thank you, Woody. Thanks for having me on today. Woody, we go back a long time, so it's always good to see you and great to be presenting today at the chapter here. So Woody, I'm also glad you mentioned the SCTE training that's available, and really good to know that you guys also incentivize people financially to take the training, because I will mention that later on in my presentation. And also thrilled to hear that you guys have a YouTube channel. I'll be mentioning that later on my training today. So that's all exciting information.
And if I may, I have to say, if you haven't seen Brady's YouTube channel, you should check it out. He has some outstanding interviews and some awesome technical training. So if you haven't been there and you want to develop your knowledge, you're missing something, because he really has some great content.
Thanks, Woody. I may just plug that in my presentation today as well.
Okay, we double plug, so forgive us.
Yeah, thank you. All right, so let's get started. If my presentation is not visible to everyone, please do let me know, but it should be up on the screen now. And as Woody, you can't see it?
I can see it, yes.
All right, awesome. Thank you for the confirmation. So as Woody mentioned, it is call it DOCSIS Showdown. Key differences between DOCSIS 3.1 and DOCSIS 4.0. I'll be covering that. It's, we're basically going to look at how industry needs and user demands are driving technology forward, and what those changes mean for us in the field. And again, I'm Brady Volpe, founder of the Volpe firm and chief product officer at OpenVault. My goal today is to translate this stuff for us. After all, the only thing that's changing faster than technology is how many tabs I have to keep open in my web browser in order to keep up with the technology. So don't feel bad if you feel like you're overwhelmed and struggling. There's just so much happening in our industry. We all got to try to stay on top of it. So here's a quick look of what we're going to be covering in today's session. I tried to include a little something for everyone. So we'll kind of start off slow, get a little bit more technical, and even cover a little pawn in today's discussion. So, why DOCSIS is evolving, some key trends, what's new in DOCSIS 4.0. I'll talk a little bit about ESD and FDX. So, if you're working for Comcast, we're going to talk a little bit about FDX. If you're working for non-Comcast cable operators, we'll talk about the technology that is being used by pretty much everyone else in the industry except for Comcast, which is the ESD, Extended Spectrum DOCSIS. Talk about some of the architecture and spectrum changes, what the technology is doing to boost capacity, not just in the downstream, but there's really an upstream focus that we're looking at. And we'll see why, the deployment timeline and transition strategies, and some of the field impacts and best practices that we want to do out there. So I start off here, and this slide is courtesy of OpenVault. Every quarter, OpenVault produces a document that kind of shows what's happening in the industry with growth and trends and stuff like that. And this shows how in recent years, broadband usage keeps climbing, particularly in the upstream. We know it does in the downstream, but there's a close relationship between downstream and upstream. And this slide's focusing on upstream growth. That we're not at pandemic levels. Like we see that spike in 2020, how the upstream had a 55%, almost 56% spike in the upstream. So we're not talking pandemic levels in upstream, but we're well above pre-pandemic levels in upstream growth. And that's important for us to realize. We're also seeing on the right-hand side, we're seeing a lot more what we call power users that are consuming more than 2 terabytes per month of upstream traffic. And these really tend to crush our networks. It puts a lot more demand, a lot more stress, especially as people are sharing a lot more high resolution videos. You got these crazy YouTube people like your chapter, like myself, that runs YouTube channels where you're not just consuming the video, but you're producing and pushing a lot of video on the network. So that's really going to tie into the theme of why the need of DOCSIS 4.0 is there as we continue to go on in our journey of cable. This next slide, also from the OpenVault OVBI report. That's the name of the report that they put out quarterly. And I recommend you guys, if you're interested in this type of data, go to openvault.com, and the OVBI report is on, I think it's on the first page when you go on there. You just have to give some personal information or make some personal information up, and you can get access to that report. And so this report is really, again, reinforcing that the trends are very clear. Higher speed tiers, like 500 megabits per second and 1 gigabit per second speed tiers, are way up just within the last year. Between 2024 and 2025, we're seeing double-digit growth on those 1 gig, 500 megabit per second speed tiers, while the lower speed tiers, under 100 megabits per second, are seriously dropping off. We're seeing double-digit drops or high single-digit declines, like 9-10% on 100 megabit, 50 megabit, and less than 50 megabit per second tiers. Figure 7 on the right-hand side, again, also from the OVBI report, is showing you can see the number of subscribers in those slower tiers is really, really shrinking. And more people are often opting for the faster plans. This means as an industry, we need to be offering higher speed plans, such as 500 megabits per second or higher, because that's what our subscribers are using and wanting to purchase. On the upstream, so we need to offer at least 1/10 of the downstream speed, meaning if you're offering a 500 megabit per second downstream, 1/10 of that is a 50 megabit per second upstream. Or if you're offering a 1 gigabit per second downstream tier, you really should be offering a 100 megabit per second upstream tier. The upstream is getting squeezed. And then there's a lot of reasons why we say 1/10. And again, we cover this so many times on the YouTube channel that I have. I'll talk about later. John Downey and I have covered this many times, but it has to do with the relationship of if you don't have enough upstream speed, you're going to throttle your downstream speed. So that 1-to-10 ratio is what we really shoot for and recommend as an industry. So these speed tier distributions that we have here, we see this again from 2024 to 2025. The amount of users that are in the 500 meg or the 1 gig tier is really starting to increase. And that's just user demand. So we have to ask the question then is, I'm sorry. So here's our first high-level comparison of DOCSIS 3.1 versus DOCSIS 4.0. And will DOCSIS 4.0 be enough to help, given the data we just reviewed in the previous 2 slides? The answer is yes. So first we can see in this first line, with DOCSIS 3.1, we already can achieve 10 gigabits per second in the downstream. DOCSIS 4.0, 10 gigabits per second, we can get 14 gigabits per second with DOCSIS 4.0, but that is really not addressing the problem that I mentioned. It's really that upstream speed. DOCSIS 3.1 gives us up to 1 to 2 gigabits per second, but it's really DOCSIS 4.0 that's going to give us that up to 6 gigabits per second. It can even give us more. We'll see later how it can give us more for that, but 6 gigabits per second on our upstream is going to start to satisfy that demand that we saw in the previous few slides, or a couple slides. DOCSIS 4.0 is really all about enabling that next leap in upstream speed. DOCSIS 4.0 does give us some other features, as we'll see in the upcoming slides, but increased upstream capacity, from my perspective, is a major focus because we can't expand the downstream without expanding the upstream for reasons that I previously mentioned. And we've seen, go ahead.
Just a second there, just a true experience. Recently had a fiber outage, right? And like I'm sure all my neighbors, we just turned on our Wi-Fi hotspot, to hop over to, it's kind of a backup. It pretty much crashed.
Yeah. Well, once everyone gets on there.
Yeah, I think my throughput went down to like half a meg in both directions because I think all my neighbors did the same thing. And it's like, there's still a really good place for us. And I checked again after the service was restored, and it bumped back up. But yeah, our consumers, they consume a lot of data, so there's a good place for us in that market.
Well, and a single household, if you have a couple of adults and a couple of kids, and they're all I'll take my wife and I as an example. We'll be streaming something on TV, and each of us will be sitting there with our phones or iPads, also streaming to our phones and iPads, because I think that is just what become of us, that you get bored with what's on TV, so now you have 2 more streams coming, and then you add in a couple of kids, also doing the same thing, it's quite easy to get a lot of data consumed into a single household. And then you deal with a whole neighborhood that's off of that same fiber node doing the same thing. And as I mentioned, you also have people that are pushing data into the upstream as well. So very quickly, it's amazing how much a single household can consume. And we see that as cable operators, as people that are dealing with that type of congestion. It's remarkable how we've changed in the industry. So yes, to your point, a single outage, you can really consume other portions of the network and cause issues. So we've seen that the demand is real, Woody, as you said, and as I mentioned, and we've seen that evolution continue, that continuous upstream growth combined with downstream speed expansion play out over the history of DOCSIS. I didn't go all the way back to DOCSIS 1 and put that on this graph. I look at just the difference between DOCSIS 3.0 to 3.1 and 4.0, and we can see that really the biggest change remarkably is upstream. We go from DOCSIS 3.0 to DOCSIS 3.1, and there is a 10x downstream increase, but a 20x upstream increase. And I think this almost like silently happens and we don't realize it because we're always thinking downstream, downstream, downstream capacity, but we've actually been increasing the upstream capacity more. And this is huge. So then from DOCSIS 3.1 to DOCSIS 4.0, we see a 3x upstream increase and no increase on the downstream. Now, so it's like, why is that? It's because that upstream becomes really important. We can't let the upstream get congested. DOCSIS 4.0 uses either extended spectrum DOCSIS, which we call ESD. You may hear people refer to that as FDD. I've really stayed to the ESD, and I think the industry's reverted back to ESD because people tend to get FDD confused with full duplex DOCSIS or FDX. Comcast has chosen the FDX path, the full duplex DOCSIS path, while most other cable operators, and at this point I really think it's the entire industry of operators with the exception of Comcast, are choosing the path of ESD. And we'll talk a little bit more what the difference is between FDX and ESD shortly. So reinforcing what we saw at the beginning of the presentation, we have a very fast downstream capacity at 10 gigabits per second, and that is from the fiber node. DOCSIS 3.1 gets us to 2 gigabits per second at the fiber node, but it's DOCSIS 4.0 that pushes us to a whopping 6 gigabits per second on the upstream. So you're already getting the concept of what the differences are between 3.1 and 4.0. A question that I get from a lot of people is, Brady, is DOCSIS 4.0 real yet? And I've been talking about DOCSIS 4.0 for many years now, but it really wasn't real because the hardware wasn't available. And we are now at the point of commercial deployment. So I have that circle. This is like the timeline of where we've been at, talking about DOCSIS 4.0 for a long time. We're in that green line that I have circled with a box. We are here. We've arrived. DOCSIS 4.0 is real, but it's somewhat limited. 4.0 modems have been available for some time, for at least a year or two. It's the CMTS platforms that have been a bit limited. They're becoming available to the larger MSOs, but inventory is somewhat limited because chip fabrication is finally getting fabricated. There's a long, drawn-out story to that, but we're finally getting there. And you've heard about the 4.0 deployments getting rolled out probably for the past year, but I think now we're going to start seeing a lot more of that because we're getting into more of a production mode. So if you're one of the lucky cable operators that actually are in the process or have been deploying DOCSIS 4.0, you also want to consider that you need to upgrade your test equipment because frequencies are changing, diplex filters are changing. You need to support more OFDM and OFDMA channels, but you also need to consider that the test equipment vendors also have the same problems of chipset availability to upgrade their equipment and push that new equipment out there as well. So that's a challenge for them. Also on the ESD and FDX side of DOCSIS. So everyone's in the same boat right now. It's just limited availability. It's going to take a little bit of time before everything busts loose, and we're kind of in the same place we are now with DOCSIS 3.1 from a DOCSIS 4.0 standpoint. So moving, do you have another question there, Woody? Go ahead. I can take a break.
No,
if not,
I was just going to say that that's interesting for test equipment, because I didn't think about that. You know, with Comcast on FDX and everybody else on ESD, you know, test equipment, you know, need to be different between the two, between Comcast and everybody else, or at least some variations. Or I don't know if they're going to include like both testing sets or just one or the other. That's strange.
And there's a lot of depends in there, right? Because Comcast in some areas uses their own completely integrated system where they use the Hytron modems. And I think still in some areas, a Comcast plant, they may use like a Viavi meter or a VX meter. Both Viavi and VX, or the test equipment manufacturers, because they don't buy large quantities, they really have to beg and borrow from Broadcom or MaxLinear or whoever they can to get these chipsets. So it's a real challenge for the test equipment vendors too. So don't beat up too hard on the test equipment vendors, because they have to get in line for these chipsets.
Yeah, this is going to be quite a challenge. But I did read something, I think it was just this week, that looked like Broadcom said they're ready to go on their FDX, or no, their DOCSIS 4.0 chipset. So it's coming. Yeah. It's going to start coming really quick now.
Yeah, and just a quick background on that chipset. What Broadcom and everyone's trying to do is create a unified chipset that has both ESD and FDX in it, which will make it easier for the cable modem vendors, the CMTS vendors, the test equipment vendors, so they don't have to buy two chipsets. They can just buy one chipset that does everything. That way, if you buy a cable modem, that cable modem would work in a Comcast system, or it would work in a non-Comcast. It'd work either for ESD or for FDX. And that's really kind of been the holdup of why it took a little longer to get these chipsets out than what we ideally would have wanted from those vendors. So that's where we're at today.
And I'd like to just remind the audience that you can post your questions in the questions box, and we'd be glad to read them out for you.
Take them at any time. All right, so we're going to move just a little bit more in a technical direction here, because I want to make sure that people understand what DAA is, because everyone's talking about distributed access architecture, but that may mean different things to different people. So, you know, DAA stands for distributed access architecture, and if we break it down, DAA is actually kind of simple. And here's so this slide I have up is courtesy of Harmonic. Thank you, Harmonic, for the slide. I didn't have to make it then. All that means is we take the brains of the CMTS, and here that can be a virtual CMTS. I'm going to show you a virtual CMTS in a little bit, or that can be a legacy CMTS that has a DAA-enabled line card in it, which means that, you know, we just took a legacy CMTS, put a card in that has a port in it that supports an SFP. So these will live either in the head end or a hub site. And then from there, we will have a digital fiber optic cable that goes to a remote PHY device, which we call an RPD. Love our acronyms in this industry. And that RPD can live either in the head end or a hub site as a remote shelf, in which case and again, the RPD is just the RF in and RF out of the CMTS. So we're taking what would normally be all the RF connectors that live in the CMTS in the head end or a hub, and we can put them in the RF shelf, or we can put them in a remote PHY node, aka fiber node. But now it's kind of a digital fiber node, because we put all those RF connectors, the RF goes in and the RF goes out. We moved that from the head end and we put it all the way out into the fiber node. So having the RPD is connected again to either the vCMTS or the DAA-enabled legacy CMTS via that fiber optic cable, which is typically running at 10 gigabits per second digitally. So there's no analog here between the brains of the CMTS and the RPD. So there's no signal degradation because, again, this is not analog fiber, this is digital fiber. So all the signals getting past that RPD are digital. Getting that RPD as close to the subscribers, so as close to the cable modems as possible. So in this case, the remote PHY or putting it in the fiber node is the best place to do it because there is less coaxial cable to degrade the RF signal, meaning we don't have any RF combiners in the head end. We don't have any RF optics between the head end or hub site and a remote PHY. That means our SNR or our MER at the cable modem or set-top box is going to be way, way better. And we're going to have less troubleshooting to do between the brains of the CMTS and the RPD. And that's just a win-win situation. This cleans up RF and gives us new options for deployment as well. And we'll see how, we're going to see how that benefits it in this slide right here. So this slide shows the end result of replacing a legacy analog fiber node with an RPD-based fiber node. Again, we took the RF out of the head end and put it right in the fiber node. This is DAA in action. And when we push the digital optics closer to the subscriber, right at the node, we get cleaner signals. SNR and MER improve. Real world data shows the average improvement of your MER is about 2.5 dB across the network after the RPD is upgraded in that fiber node, with a maximum improvement in this specific use case of 8.2 dB on our, whether you call it SNR or MER, it's the same. And also, you can see how the histogram of all the MERs or SNRs of those modems on that node tightened up. I personally would rather be responsible for maintaining this fiber node rather than this fiber node on the left-hand side, because we see there's a lot of modems that have low SNR or low MER, and we know those are going to be problematic modems. They're going to be bouncing offline, they're going to be flapping. Subscribers will be complaining about uncorrectable code words. They may not complain about that unless they are familiar with them, but they'll be complaining about slow data issues, gaming issues, voice issues, video issues, etc. So it just improves the plant a lot. So other things that we can do, let's talk about if you have a 42 megahertz system today and you're running 4 SC QAMs. The maximum upstream that you could possibly get if you didn't have any impairments would be 108 megabits per second. Once you upgrade your plant to DOCSIS 3.1, you start to get a lot of options. You could drop a couple of your SC QAMs and drop in a 19.2 megahertz wide OFDMA channel. Again, just a 42 megahertz plant. Suddenly your upstream capacity on that fiber node jumps up about 70 megabits to 170 megabits per second. Or if you had all DOCSIS 3.1 modems, you could get rid of your SC QAM channels altogether, and now you more than double, you almost triple your upstream capacity to 280 megabits per second just in a 42 megahertz return plant. So again, there's lots of options with DOCSIS 3.1. You guys probably already are familiar with that. I didn't even mention the capability to simultaneously support SC QAM and OFDMA on the same frequencies, which is called TAFDM. There's reasons why you may or may not want to use that technology because it creates some additional overhead, but if you need it, it's there and it's supported in the DOCSIS 3.1 spec. Now let's talk about 85 megahertz because a lot of operators are starting to upgrade their return path to 85 megahertz. So here you could have OFDM and your 4 SC QAM channels running, deploy OFDMA in the lower frequency where it's really noisy and maybe 11 megahertz down here, another 43 megahertz taking you all the way up to 85 megahertz. You can get almost 500 megabits per second of capacity, assuming you don't have a lot of noise. Or you could drop those SC QAMs altogether. You could get over 500 megabits per second. Again, assuming you're running at 1024 QAM and don't have a lot of noise in your upstream. So you might be asking, why do you have that 11 megahertz block down there? I would recommend running that smaller OFDMA block in the noisy part of your low frequency spectrum, where I have that 11 megahertz block of OFDMA. Your plant may require larger block here. If you have more noise, you may want to slice this split here differently. And the reason is this will allow your modems to still use this smaller OFDMA block in the noisy spectrum, but at a lower order modulation. The larger OFDMA block will ideally be usable by the cable modems, but at a higher order modulation, because this, somewhere above 20 megahertz or so, you always see the noise drop significantly in the return pass. So this can operate at a much higher order modulation. You get much higher data throughput, and that's ideally what happens. Of course, the best solution would be to deploy a technology called the profile management application, which would adjust the modulation across this entire band automatically, dependent on exactly where the noise is. But that's an entirely different presentation to get into how profile management application works. There will be a couple presentations at SCT Expo this year, if anyone's attending, that talks about how PMA works, particularly in a DOCSIS 4.0 network. On this next slide, we can see the natural upstream frequency progression from 42 megahertz to 85 megahertz, all the way to 204 megahertz, and how we see our upstream growth, 300 megabits per second to 684, to 1.8 gigabits per second on the upstream. And that's some serious bandwidth, again, just in the DOCSIS 3.1 network. We'll see DOCSIS 4 on the next slide. The billboard number that I have on this slide is typically the speed tier that a cable operator may offer to their subscribers once a given PHY rate has been achieved. So note that once you get your return upgraded to 204 megahertz, it's very possible to start offering 1 gigabit per second symmetrical speeds to your subscribers, which can be important, especially if you have a fiber competitor in your market. So I know a number of cable operators that once a fiber competitor has come in, like this is a key thing to do, to upgrade to 204 megahertz, and you can start directly competing with that fiber operator with 1 gigabit per second symmetrical speeds. So DOCSIS 4.0 enters the room. With DOCSIS 4.0, the frequency spectrum extends to 1.8 gigahertz. So that's a big change with DOCSIS 4.0. Even higher frequencies can be supported in the DOCSIS 4.0 spec, but we won't get too crazy talking about 3 gigahertz in this presentation today. With DOCSIS 4.0, you also get a number of different diplex filter frequency splits in the ESD, the extended spectrum DOCSIS side. So you get like a 204, 258 diplex filter split. This is, and when I'm talking diplex filters, this is like your 42 megahertz, 52 diplex filter split, your 85 megahertz DOCSIS diplex filter split. When you go to 4.0, so 204 would be your diplex, 204, 258 would be the last diplex filter split that you have for 3.1. With 4.0, we get the 300, 372, 396, 492, 492, 606, 684, and 834 diplex filter splits. And each one of these gives you different downstream and upstream speed tiers. Industry leaders predict that the most common diplex filter split we'll be looking at is the 396.492, because that gives us a 10 gigabit per second downstream and a 2.5 gigabit per second upstream. On the FDX side, so the full duplex DOCSIS that Comcast looks at, we have a 7.5 gigabit per second downstream and a 5 gigabit per second upstream. But full duplex DOCSIS does not have a fixed diplex filter like the ESD spectrum does, the top spectrum. So there's a lot more flexibility in FDX than there is in ESD, of like, you know, how we, if we needed more upstream speed, we could trade off downstream speed for that upstream speed. So that is a benefit with FDX over ESD. But whichever option you go with, when looking at competing head-to-head with 10G PON, the fiber technology that we're dealing with, true speeds on that are typically around 7.5 gigs symmetrical, coming from the OLT. That's the device that lives in the PON head-end. DOCSIS 4.0 is very well positioned to compete, provided we keep our plants well maintained. So what is the big difference between DOCSIS 3.1 and DOCSIS 4.0? Other than behind the scenes security tweaks, and there's actually a lot of security tweaks that come, and security improvements that come with DOCSIS 4.0, it's mostly about higher frequencies, particularly on the extended spectrum, the ESD side of DOCSIS. Again, we go up to 1.8 gigahertz, which means we can add more OFDM channels, and because we have higher diplex filter splits, we can add more OFDMA channels. We're not limited to 204 megahertz. And that results in higher speeds, especially in the upstream. FDX DOCSIS, or full duplex DOCSIS, that already existed in the DOCSIS 3.1 specification. So, you know, the differences between DOCSIS 3.1 and DOCSIS 4.0, that was, FDX was already there in DOCSIS 3.1. So, you know, 4.0 was not a big revolution with us for full duplex DOCSIS. A word of caution to all my technician friends: with those higher frequencies going to 1.8 gigahertz or maybe even 3 gigahertz later on, we're going to get some new RF headaches that we have not seen before. For those of you who are old enough to remember how we did not have to deal with things like standing waves very often, when we had a 550 megahertz plant. Yes, 550. Some of you may even remember 350 megahertz plants. As we have migrated to higher and higher frequencies, like 1 gigahertz, some really gnarly RF issues suddenly became important for us to deal with and mitigate. Well, just imagine what it's going to be like when we almost double that frequency to 1.8 gigahertz. I'm not saying we're going to double the amount of RF impairments we have to fix, but I'm also saying that we're not. It's going to be a brave new world with some of the new things that we have to deal with moving forward. So, yeah, it's going to be fun times. So, in some recent live streams, and thank you, Woody, for plugging this earlier, with Ron Rannick and others, we've talked about how to measure OFDM on DOCSIS 3.1 meters. I've not had a DOCSIS 4.0 meter yet, and this is some key stuff that every technician should be acquainted with and comfortable with these basics. So, again, plugging my YouTube channel, if you want to see more of these and you want to see, Ron has done some amazing videos on just like RF basics. We've covered DOCSIS troubleshooting, everything up to the latest on HFC and fiber. Our last episode, we even covered how you can extend PON out of a remote PHY device. So we cover a lot of different technology. We love recommendations. So if there's something we haven't covered on a topic you'd like, just let us know. So you can just go to YouTube and search on the Volpe Firm, or go to youtube.com/Volpe Firm. Check us out. The next few slides that say compliments of Ron Rannick on the bottom here. These are from a slide, one of our live streams that Ron put the presentations together. So I pulled a couple of these slides out, but I think these are some really, really important fundamentals of understanding how to visualize and just troubleshoot some basics of OFDM. So I just pulled some of these out, and I want to give Ron credit for these, but I think these are really, really important basics as we go through these. On this particular slide here, I've circled this OFDM channel. The DOCSIS specification, part of the DOCSIS standard, provides a measurement to break up the OFDM channel into 6 megahertz chunks and display the power of that OFDM channel in 6 megahertz chunks. And this makes it easier for technicians to measure that OFDM channel and compare it with a 6 megahertz blocks of SC-QAM channels. When you hover or select that OFDM channel, the meter will display a label as to which channel type it is, in this case, OFDM. Make sure that you can quickly analyze both types of channels, SC-QAM and OFDM, during your field testing. Once you've selected an OFDM channel, check the bandwidth. Here you can see the OFDM start frequency is 672 megahertz right here, and the end frequency is 768 megahertz right here, resulting in an OFDM channel that is 96 megahertz wide. So an OFDM channel it's not a fixed bandwidth, it's not a fixed width. It can have many widths, starting all the way down from about 24 megahertz up to 192 megahertz. So that might be something you want to do as part of your validation of your OFDM channel. Another important aspect of the OFDM channel is something called the physical link channel, or PLC. In this example, the PLC is located at 717 megahertz. And the PLC is absolutely critical for modems to lock on and stay locked to the OFDM channel. Severe noise or signal issues, or if you have like a suck out where that PLC is located, will prevent modems from locking on or staying locked to the OFDM channel. So we always recommend inspect the PLC location carefully, but to do so, you need to know what the PLC is and also where it's located.
I do have
yeah, go ahead.
So Sean Anderson asks, what is the expected upstream and downstream speeds in full DOCSIS 4.0 with exclusions built into the FM and LTE bands to help mitigate off-air ingress?
So there's a lot of depends in there, but let's talk about exclusion bands first. So if we looked at this OFDM channel here, what is an exclusion band and why would we use it? An exclusion band gives the cable operator the ability to turn off subcarriers. So within that OFDM channel, there can be thousands of subcarriers. In a 192 megahertz channel with 25 kilohertz subcarrier spacing, you'd have like 8,000 subcarriers, 8,000 little tiny channels, each one transmitting subscriber data. If within that 192 megahertz wide OFDM channel, we know, well, I put my channel right where right in the middle of the LTE band, and we know the LTE band. Let's say it's right around 700 megahertz, and that LTE band falls right where my OFDM channel is, and the LTE band, let's say it's 10 megahertz wide, or there's 10 megahertz of interference that I routinely see is interfering with my OFDM channel. Well, as someone who manages the CMTS, I can go in and say, you know what, I'm just going to turn off those 10 or 20 megahertz of subcarriers within my OFDM band. Now, I can turn them off And what that means is if I left them on, first of all, my modem is going to see uncorrectable code word errors, and eventually it's going to see enough of them that it's going to either drop to a very low order modulation, which means now the speed that my modem can receive data on that OFDM channel is going to be slow, or worst case, my modem won't even be able to stay locked to that OFDM channel. So now all the time that I took to get my 3.1 modem up and running on the OFDM channel has been wasted. My modem's going to fall back into DOCSIS 3.0 mode and just use the SC-QAM channels. So what I do is I can just turn off the subcarriers that are being impacted by that RF impairment from LTE. LTE's used by our cellular phones to talk to the tower. So if I turn them off, just the subcarriers that are being impacted, all the other subcarriers will still transmit data to the cable modem without any problem. And this isn't something that we can do with our legacy SC-QAM. Remember, legacy SC-QAM, it either works or it doesn't work. You get a bunch of uncorrectable code word errors, and that SC-QAM channel is useless. Not the same with OFDM. We can turn off individual subcarriers. That's called an exception or exclusion band. So the question is, what is the impact? How does that reduce my data rate? Well, there's a calculator, and if you go to, actually, I don't have it on my website yet, I will soon, but if you go to github.com/Brady Volpe, you'll see that I have a OFDM and OFDMA calculator on there. In that calculator, you can actually calculate the speeds. So if I'm running a 4096 QAM, here's my bandwidth, here's my exclusion band. You can calculate the actual capacity because there's a lot of variables because OFDM has multiple modulations that the cable modem could lock onto. If you did not have that exclusion band in there, maybe the modem would be only able to run at 256 QAM, which would give you a very different speed than if you put that exclusion band in, and now the modem's able to run at 4096 QAM. You'd get a very different speed there. So I couldn't tell you the exact speed without taking you to that calculator. So it depends, but I hope I partially answered your question with explaining the exclusion band and why we use it. So now I wanted to reinforce again what this shows you here is it shows you the OFDM channel broken up into 6 megahertz chunks. It shows you, and this is taken from, most meters are going to show you how to do this, where you can measure your average power level, your minimum power level, your maximum power level. And this is important because, again, you may have too much tilt on your OFDM channel, or you may have a suck out or some other impairment on your OFDM channel that's preventing your cable modems from locking onto that channel. And this is one way to visualize it. So knowing how to use your test equipment, whether that's a P&M application, a reactive application, or a test meter, is really important to see that. An even better way, and I think this is one of the best ways to look at both your SC-QAMs and your OFDM channel, is to use full band capture. And this, again, this can be done in the P&M application, reactive application, on a test meter. Full band capture is available in DOCSIS 3.0, DOCSIS 3.1, DOCSIS 4.0 modems. It's like having a spectrum analyzer in every subscriber's home. This is one of the best ways to visual downstream RF spectrum in high resolution. So any issues like standing waves, tilt, suckouts, resonant peaks, and more are going to be visually visible to you when you're doing troubleshooting. And these are going to be either outside plant impairments, drop-related plant impairments, connectorized or in-home plant impairments, all of which you're going to need to troubleshoot as technicians so you can make sure the plant is clean and your subscribers are your 1 gigabit per second or 2 gigabit per second to your subscribers are able to actually achieve those speeds. Now, for me, the most important thing that I look for on a subscriber's modem is uncorrectable code word errors. Everything can look great, but if you still have uncorrectable code word errors, especially a lot of them, then there's still a problem. Here we can see there are no uncorrectable code word errors on our PLC. And remember I said that PLC is really important to make sure the modem can lock to the OFDM channel. And we also have no uncorrectables on what we call Profile A. Now, I'll talk about Profile A and Profile B in the next slide. We do see we have a correctable code word errors. We're almost always going to see correctable code word errors on an OFDM channel because it's using a correction method called low density parity check, LDPC. Don't worry about correctables. We're almost always going to see correctables in a DOCSIS 3.1 and 4.0 world on our profiles. Correctables are expected. It's just part of the way that works. Don't worry about them. Here, so a lot of meters, a lot of P&M applications are starting to show you different profiles. So I mentioned before that we will have different modulations on our OFDM channel. Also have that on the OFDMA channel on the upstream. Profile A is going to be our slowest profile. So if your modem is only locked to Profile A, that means it's using the slowest speed that it can on the OFDM channel. Our next profile, and this is typical, Profile B will typically be your next fastest profile, and you may also see like Profile C and Profile D. These are typically going to be faster profiles with higher order modulations all the way up to 4096 QAM. The modem, the cable modem, will automatically select the best profile based on plant conditions. Any profile having uncorrectable errors will almost definitely not be used by the cable modem. And remember, more profiles usually means better adaptation to plant impairments if correctly configured on the CMTS, because if there are more modulation options available to the cable modem, then the cable modem has more options to choose from when noise is present. And again, PMA will dramatically improve overall performance, and that's going to be covered this year at Expo. Finally, I want to point out the average RxMER per subcarrier as an important indicator of the OFDM channel's performance. In this case, it's 41.3 dB, which is a solid value capable of supporting 4096 QAM. But be mindful, it's actually the worst case 10% of a subcarrier that matters. In this case, in the way it's displayed in this meter, it's MER percentile 2, which is 2%. That is your worst 2 percentile, showing 39.5. Still, that's a great MER. It's going to support 4096 QAM, but it's the worst 2 percentile of subcarriers that typically controls what profile the modem will likely use, and if low enough, whether or not the modem can even use that OFDM channel. So you kind of always, again, this is understanding the test equipment or the software application that you're using to understand average versus worst. It's the worst that really matters. So what I just talked about and talked through are what I considered the must-knows for DOCSIS 3.1 and DOCSIS 4.0 OFDM downstream troubleshooting. Don't forget, we have the upstream component for OFDMA, but you got to get the training. Woody talked about this at the very intro. Use PNM, ask questions, and take SCTE courses. The SCTE has a great number of courses that can help bridge any skill gaps you may have, but you got to ask. You got to ask for some help. Most of these courses are self-paced and also may be covered by your company or even your chapter, like Woody mentioned. You just need to ask and never stop learning because our industry keeps evolving. Woody?
Yeah, and while we're paused here for a second, I'm going to launch a question to the audience so you guys get a chance to participate. So here we go. Let's see. What is the key technology advancement in DOCSIS 4.0 that allows for increased upstream capacity? I think Brady covered this a little earlier. So hopefully you guys, unlike me, have a memory and can answer this. So we do have some people taking votes. I'll pause for just a second and just remind everybody, if you have any questions, don't be like Sean. Oh, I do have a question here. the question is from Chris Hawthorne, and this is probably for me. Will this webinar be available on the SCT Golden Gate website afterwards? Yes, but I can't tell you exactly when. I would give it a couple of weeks, and the SCT changed the setup a little bit from where it had been previously. But if you just go to the events calendar and you go to this event in the calendar, or this event in the calendar, you will see a link to the training so you can replay it. So I would give it a couple of weeks before you attempt that. That's going to change next year. We're actually going to have a different platform, and I'm not sure exactly how long it'll take to make it available, but I think it'll be a lot quicker. So you can go in there and replay the webinar session fairly quickly after we're finished. So we got 26% voted, folks. So if you guys could get in there and get your vote in, it'll be interesting to see what you all come up with. So we have 4 possible answers: dual carrier modulation, OFDM aggregation mode, full duplex DOCSIS, and downstream echo cancellation. So we got some options here. 42%. I think I'll wait till we get to at least 50%, and then we will close the poll. So we're at 49% now. Give it just another second. There we go, 51%. So I'm going to close the poll, and then we will show the answers, I think. Let me see. So it looks like...
Excellent. They got it right. It is full. So we have, with DOCSIS 4.0, we have either ESD, extended spectrum DOCSIS, or full duplex DOCSIS, FDX, that's the enabling technology that increases our upstream speed. So great job. Yes. Most everyone got it right.
Everybody was paying attention. So we'll hide this, get back to the presentation, and we have 2 more questions. So take notes.
Yeah. All right, and I'm going to I'm getting close to, as normal, I go over quickly, so I'm going to go pretty quick on this last part here. I wanted to briefly touch on PON, because a lot of us have PON in our networks. If you're new to PON, don't worry, there is a tie into DOCSIS, I promise. This is the big picture. The OLT, or optical line terminator, connects over fiber. A fiber splitter, so you have 1 input, many outputs to ONUs, or optical network units, at each subscriber's home or business. Just substitute cable modem for ONU and CMTS for OLT, and you've nailed PON technology so far. So there's just no coax cable involved. It's a fiber-rich diet. Skip this one. Actually, I will go back to this. There is something called Open ONT. This slide is courtesy of Harmonic, but what it gives us the ability to do is have PON and DOCSIS coherently exist. There's no sound for this. I'm just going to quickly show what's going on here. This device right here that I'm pointing for, hopefully you can see my mouse. If not, it's the one above my elbow with a blue horizontal light. That is a VCMTS. It's just a 1U rack mount device. And then right above that is a shelf mount RPD. But what I'm going to do here is I'm going to take, you see that device in my hand, that's called an SFP, a small form factor pluggable. I'm just going to plug that right into the RPD. And when I plug that into the RPD, it now becomes an OLT and a CMTS. So right there, this fiber here going in is the 10 gigabit optical fiber that powers the RPD. And you can see fiber coming out and in, or coax cable coming out and in, which is serving my DOCSIS network. But with this OLT that I just plugged in, you can see I'm plugging a piece of fiber into it right there. And that fiber runs to a splitter, which then can go to multiple ONUs. So now I have one RPD here, and this RPD is running in the shelf. But imagine if this RPD was running like in a fiber node, And this is an example of a fiber node with an RPD in it. I could plug that same SFP into the fiber node. And now this is an example of fiber nodes that are serving cable modems from the same VCMTS, and also running a PON network. So this gives us so many cool options of what we could do when we think about our DOCSIS networks. So we have a DOCSIS network, we have provisioning, we have our fiber node already deployed out there, but maybe we have a business nearby like a Starbucks, and that Starbucks has been running a cable modem, but they're like, hey, we are just not getting, we don't have enough speed. We need to upgrade that speed. Could you give us a device that's running, maybe 5 gigabit per second bidirectionally? Well, a cable modem just can't do that today. But if we pull that fiber into that Starbucks and replace the coax with a fiber and dropped an ONU in there, now that Starbucks could have 5 gigabit per second symmetric data capabilities, because we're already running a 10 gigabit per second fiber to the fiber node. So I'm really excited about this technology of running PON plus DOCSIS together. Gives us a lot of capabilities. Maybe we just wanted to even do a node split. We could run a fiber to another node because we needed another fiber node in that area. This, to me, is really cool innovation that we are doing as an industry, giving us more capabilities. And because this is built on open ONT, granted, this is something Harmonic is doing, obviously, right now, but any vendor can do this if we want this as an industry, if we as cable operators start deploying it. So just wrapping things up. Oh, go ahead, Woody.
I do have another question.
Yes, sir.
This one is from Tony Holmes. How does it work when there are multiple orders of modulation in a single profile? Comcast does this a lot. Example, profile B having 1K and 4K 256.
Yep. So, and that is the way all OFDM and all OFDMA channels work. They're going to have multiple profile options that are available for the cable modem to use. Let's say 256, 1024, 4096, 3 profiles. The modem and the CMTS will negotiate back and forth, and let's say that there's no impairments between the modem and the CMTS. The modem will use 4096 QAM because no impairments. Now something happens in the cable plant and an impairment will arise, and that modem will see the impairment. The modem will drop down and see, well, let me see if I can use 1024 QAM. So the pipe, at 4096, we have a lot of capacity. That's a very fat pipe going into that cable modem. When the impairment arises, the modem may drop down to 1024 QAM. If the impairment's too great, it may drop all the way down to 256 QAM. So now the amount of data capacity that can flow into that modem just gets smaller. 256 QAM is lower bits per second per hertz than 4096 QAM. So that negotiation will drop down while that impairment is present. Ideally, you'll have tools available to you to show that modem's dropped to a lower order modulation, especially if it's a gigabit per second tier. We go out, we fix the impairment, and now the modem will go back up to the capability to operate at 4096 QAM. So it's sort of a dynamic thing where the modem can go back and forth between the different modulations depending on the impairments that are present that the modem is seeing.
And Sean Anderson has a similar question. We may have answered that, but in case we didn't, is there any customer impact when a modem demodulates down to a different OFDM or OFDMA profile due to impact to the carrier?
Yeah, so I think you kind of asked me the same question. If the customer's modem was running at 4096 QAM and now it drops down to the 256 QAM modulation, is there any impact to that subscriber? That depends. If that subscriber is only paying for a 50 megabit per second tier, they're probably not going to notice, because 256 QAM modulation plus the SC QAM channels that modem is locked to, they're going to have plenty of speed throughput. However, if that subscriber is paying for a gigabit speed tier or a 2 gigabit speed tier, which some cable operators are offering now, they may notice the difference, because when they go to hit their speed test, which is the killer app that all subscribers are using right now to test their speed, they may not get a gigabit per second or 2 gigabits per second if they are now dropped all the way down to 256 QAM. Or in a worst case, if the impairment's bad enough, their modem may go into partial mode, not even be locked to the OFDM channel. Now they're just locked to SC QAM channels, which maximum they're going to get with 32 SC QAM channels may only be a gigabit per second, which they're sharing with every other 3.0 and 3.1 modem on that channel. They're probably not going to get that gig speed or 2 gig speed that they're getting. So that would be the impact to the subscriber.
And I have 2 more questions I need to launch. Is now a good time, Brady?
Absolutely. This is my last slide, so everyone can read the wrap up, and I won't even cover it.
Okay, so let's see this one. So, how much downstream spectrum can extended spectrum DOCSIS support compared to DOCSIS 3.1? We have 4 possible answers. 1.2 gig in 3.1, 1.2 gig in 3.1 up to 1.8 gigahertz in ESD, 1.0 gigahertz in DOCSIS 3.1 up to 3 ESD, and 1.2 gigahertz in DOCSIS 3.1, same in DOCSIS 4.0. So we'll give a minute for everybody to vote and see where we're up. We're up to 23%. Did anybody have any more questions? Yeah, I don't see any more questions, but feel free to ask questions at this time.
Yeah, while they're answering, I'll just cover this last speed. So the last slide, the wrap up here. As we talked about at the beginning, one of the drivers for DOCSIS 4.0 is a subscriber demand for upstream speed, and we see that continue to grow year over year. But I mean, there's a relationship between upstream speed and downstream speed. Obviously, the demand for downstream speed continues to grow, and we can't just continue to increase the downstream without increasing the upstream at that 10-to-1 ratio of the downstream. So that's why the upstream has to continue to grow. DOCSIS 3.1 and 4.0 differ mostly in that increased frequency. So, we see an increased frequency in both of them. However, troubleshooting at higher frequency, as I mentioned earlier, I really expect to see some really cool things that happen as we go to higher and higher frequency. Things that, like I said, when we saw at lower frequencies, there was a lot of RF impairments we didn't see at the higher frequencies. So you get the poll results back, Woody? There we go, 77%. Guys, you nailed it. Good job. Everyone was paying attention. 1.2 gigahertz in DOCSIS 3.1 and up to 1.8 gigahertz in ESD. That is the required. I did mention there is there is a 3 gigahertz option, but it's something that is really, I think, a wish right now. We'll see how that plays out over the coming years.
That's down the road a ways, I think.
Yes.
We have one last question. We didn't cover this too much, I don't think, but everybody can take a stab at it real quick. Which of the following is a development challenge unique to full duplex DOCSIS? This might be a little hard if you're not in a Comcast network where...
Correct. Yeah, and I really didn't cover this question in the presentation because I thought there would probably be people on this presentation that may not be using FDX. And if you're not using FDX, you're probably not aware of this answer.
Yeah, well, we'll just we'll give it a minute here. We're up to 17%, so I probably won't let it run up too high. Because a lot of people are voting, so we'll give it a second. Anything else you'd cover while we're for everybody?
No, I think we covered everything. Just I'd like to thank everyone for attending today. Appreciate everyone's time. I hope everyone got a little bit something out of this presentation. If not, let me know.
Yeah. So this
58% of the people. 58% of this people were familiar with node plus zero architecture with echo cancellation. And I will add to that, there has actually been node plus zero architecture is no longer required with FDX. There are FDX capable amplifiers out there now that enable us to go more than node plus zero, where we can amplify full duplex, which I think gives full duplex a lot more capabilities than what node plus zero does. But the echo cancellation is pretty required in full duplex DOCSIS. So, good job, folks. Great job on the poll questions. Thanks for listening.
And just like to thank everybody for joining. I'd like to thank Brady for this awesome presentation. And I hope everybody has a wonderful day. Thank you, everyone.
Likewise. Thanks for having me.